This video is about mathematical induction, a method of proof that we will use to show that the sum of a sequence is true for any number of terms in the sequence. Mathematical induction in general is a method for proving that statements involving natural numbers are true for all natural numbers being 1, 2, 3, etc. Imagine a set of dominoes set up in some sort of a pattern involving a chain. You know that if you touch the first domino, push it over, it will knock into the second domino, and the second domino will knock into the third domino, and so forth until all the dominoes fall. Mathematical induction is like the domino effect. We show that some statement, in this case the formula for the sum of a sequence, is true for the first term. Then we show that if it is true for any certain number of terms, it's always true for the term after that. Consider the statement the sum of the first n positive odd integers is n squared. In other words, 1 plus 3 plus 5 plus 7 is equal to the number of terms squared. So is this true? If we try it out for the first 5, let's think about this. 1 is 1 squared. 1 plus 3 is 4, which is 2 squared. 1 plus 3 plus 5 is 9, which is 3 squared. If we add 7, it's 16, which is 4 squared. If we add 9, it's 25, which is 5 squared. Let's try it for n equals 8. So if we add up 8 terms, it equals 64, which is 8 squared. So we might think, wow, that's enough to convince me that this always works. But unfortunately in math, just knowing that it works for any number of terms doesn't mean that I could go 1,000 terms, 2,000 terms, 3,000 terms, 1,000,000 terms, and the formula would still work. I can't assume that it works just because I've demonstrated it to my satisfaction by trying a few examples. I have to prove it using a general formula for any term. So that's what we're going to do with mathematical induction. So first of all, we need to write a formula for the nth term. Since we're just looking at specific numbers here, we need to know a general term. So we would write 1 plus 3 plus 5 plus 2n minus 1. Well, let's just convince ourselves that 2n minus 1 is the term generator formula to build the nth term. So for example, for number 9 is the 5th term in the sequence. 2 times 5 minus 1 is 9. 13 is the 7th term in the sequence. 2 times 7 is 14 minus 1 is 13. So in other words, if I plug any number for n in here, I'll get the nth term. Then n squared, and I don't know why this keeps doing this, so I'm going to have to keep turning it off. It's annoying me. Keep the currents. There we go. Keep the current color scheme and don't show this message again. The unedited version with annoying pop-ups. Okay, let's move on to the next slide. Once again, we see 1 plus 3 plus 5 plus 2n plus 1 equals n squared. 2n minus 1 is the term formula. Okay, that's the same as when we did a sub n equals, and you can see this is an arithmetic sequence, and 2n minus 1 is a linear formula, so that makes sense. N squared is the sum formula. So that gives us the sum s sub n. And that's important to remember when we're doing these problems. First of all, we need to show that the statement is true for n equals 1. So we're going to put 1 into the sum formula, we're going to put 1 into the term formula, and we're going to see that the sum equals the first term. So in other words, 2 times 1 minus 1, there's our term formula, equals 1 squared. Well, yes, that's true, because 2 minus 1 is 1, and 1 squared is 1, so they're equal. So we have shown that this formula up here, 1 plus 3 plus 5 plus 2n minus 1 equals n squared, is true when n is just 1. Now we want to show that if n is some other term number, that the formula is going to work. Actually, we're going to assume that if it is true for some other term number, we're going to call that term number k, then it will also work if n is equal to k plus 1. So in other words, we're trying to show that if the thousandth term works, then the thousandth and one term would also have the same sum formula. So let's look at this kind of practically speaking. Going back to our sum formula. First, we assume the sum formula is true for k terms. In other words, I'm just taking n and substituting k. The reason I'm substituting k for n is k represents any term number. Since it's not a specific number, I can say that k represents any term number. And we're going to say, let's assume that this is true. Now you might think, why can we assume this is true? Well, we're going to do an if-then statement. It will make sense when we get to the end. Now we're going to add one more term, the k plus 1 term. So notice on the left-hand side, we have 2k minus 1 plus 2 times the quantity k plus 1 minus 1. So notice here, in this part, n is equal to k, but in this part, this is 2n minus 1, but in this case, n is k plus 1. And here we have n squared, and we have k plus 1 squared. So we're saying, let's add one more term to this previous statement and see if it's really true. So notice that is the k plus 1 term, and this is the sum formula with k plus 1 subbed in. From above, right here, we know that the sum of k terms is k squared. So in other words, 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 equals k squared. So we're going to do a substitution. We're going to substitute k squared for all of this that's highlighted in gray here. So notice now we have k squared plus 2k plus 1 minus 1 equals k plus 1 squared. Now all we have to do is show that the left-hand side equals the right-hand side, and we have completed the proof. So let's multiply everything out and show that both sides are the same. So if we multiply this out, we get k squared plus 2k plus 2 minus 1. K squared plus 2k plus 1. If we use FOIL over here, we get k squared plus 2k plus 1. So what's our conclusion? The conclusion is the most important part of this proof, because if you don't understand what you did and why you did it, then you really don't understand this proof. So it's very important. It's so important, in fact, that I will make you explain the conclusion at the end of the proof. And so you need to be able to write this out for yourself and understand what it means. So conclusion. Now the part in the purple here is just relating this back to the domino example, so you don't have to write the purple part in your conclusion. Conclusion. I just proved that if 1 plus 3 plus 5 plus 2n minus 1 equals n squared for k terms, then the sum formula is also true for k plus 1 terms. So I said if that previous statement is true, so if, I'm going to go back to my previous page here, if this statement I made here is actually true, then when I add one more term to it, it's still true. So I just proved kind of an if-then statement. So what I proved was that each domino knocks over the next one in the chain. But that doesn't help me unless I can get the chain started. So that's my first step. I also showed that the sum formula is true for the first term. Remember, we plugged in 1 for 2n minus 1. We plugged in 1 for n squared, and we showed that when n is 1, then this is true. There's one term, 2n minus 1, and there's 1, and the sum is n squared. We showed that that was true. So that's like knocking over the first domino. Therefore, since the sum formula works for the first term, then I know it works for 2 terms. Why do I know that? Because of the second part. If it works for k terms, then it must also work for k plus 1 terms. So if it works for 1 term, it works for 2 terms. Since I know now it works for 2 terms, then it must work for 3 terms. It works for 3 terms, 4 terms, and so forth. So continuing that chain of reasoning, 1 plus 3 plus 5 plus 2n minus 1, oops, I went ahead of myself here, equals n squared. 1 plus 3 plus 5 plus 2n minus 1 equals n squared is true for all values of n. In other words, I've just knocked over all the dominoes. So let's summarize. The way we do mathematical inductions is we show that whatever statement we're trying to prove and we're going to be doing it for some formulas in particular, is true for the first term, for n equals 1. Then we show that if the statement is true for n equals k, then it is also true for n equals k plus 1. Putting those two together means it's true for all values of n. So, practically speaking, if we are proving sums of sequences, this is what we do. First of all, we prove that a sub 1 equals s sub 1 because s sub 1 is just the same as a sub 1. It's the sum of one term, the first term. Then we write out the sum formula for k terms, and we add on the k plus 1 term and show it is equal to the sum formula at k plus 1. So symbolically we say that s sub k plus a sub k plus 1, the sum of the first k terms, plus the next term, a sub k plus 1, is equal to the sum of k plus 1 terms. Algebraically show those two are equal, and we've completed the proof. So let's look at another example. Here we have 1 plus 5 plus 9 plus 4n minus 3 equals n times 2n minus 1. Now, show that it works. This shows that the statement works for n equals 1. So in other words, we want to show that a sub 1, that's our formula for the term a sub 1, because we're going to look if we put in 4 times 1 minus 3, we get 1, equals s sub 1. Now let's just stop for a second, first of all, and convince ourselves that it even works at all here. So let's just add up the first three terms. 1 plus 5 plus 9 is 15. That's the sum of three terms. So this should be s sub 3. So if I put in 3 here, 3 for n, I get 3 times 6 minus 1. 3 times 5 is 15. That's the sum of the first three terms. So it appears to work. So I start out by showing that it works for the first term. Plug in 1 in the sum formula and in the term formula, and I get 1 equals 1. Okay, so it does work for the first term. Now, assuming it works for n equals k, show that it works for n equals k plus 1. So in other words, show that the sum of the first k terms plus the k plus first term equals the sum of the k plus 1 terms. So here we go. The sum of the first k terms, using the sum formula up here, I substituted k for n. K times 2k plus minus 1 is the sum of the first k terms. Then I add the term in the k plus 1 position. So that means I put k plus 1 in for the term formula right here. And then I'm saying that should equal the sum of k plus 1 terms. So I'm going back to the sum formula over here, putting in k plus 1 for n here and here. Show that algebraically that these two sides are equivalent, and I'm done. So simplifying this gives me 2k squared minus k plus 4k plus 1 minus 3. I'm sorry, plus 4 minus 3. So that simplifies to 2k squared plus 3k plus 1. If I multiply this out, this is 2k plus 2 minus 1, or 2k plus 2 minus 1, 2k plus 1 times k plus 1. If I multiply that out, I get 2k squared plus 3k plus 1. You can do the algebra and demonstrate to yourself that that works. Okay, conclusion once again. Let me go back to here. I've demonstrated that if that s sub k is equal to the formula that I claim above, and I add one more term to it, then it is also true for k plus 1 terms. Now, last example, same thing as what we've done before, only the algebra is just a little bit more complicated. Here we have a geometric sequence. 1 times 5 is 5, times 5 is 5 squared, times 5 is 5 cubed, etc. So the nth term is 5 to the n minus 1. Okay, second term would be 5 to the 2 minus 1, which is 5 to the first. We're showing that the sum of the sequence is equal to 1/4 times 5 to the n minus 1. Where does that come from? If you actually use the geometric sum formula, a sub 1 times 1 minus r to the n over 1 minus r, and just do a little rearranging of it, you'll get this formula right here. So let's just demonstrate to ourselves that it works for three terms. 6 plus 25 is 31. So if I put in 3 here, I get 5 to the third is 125. 125 minus 1 is 124. 124 times 1/4 is divided by 4 is 31. So that works. Okay, first step of the proof. Show that it works for n equals 1. Plug in 1 into the term formula on the left, and then plug it into the sum formula on the right. So I have 5 to the 1 minus 1 is equal to 1/4 times 5 to the first minus 1. Once again, 1 equals 1. We happen to be doing a lot of examples where the first term is 1. This only says 1 equals 1 if the first term is 1. If our first term was 5, we would want it to say 5 equals 5, for example. So don't assume it's always going to be 1 equals 1. It just happens to be the sequences that we've been using. Now we want to assume that if the sum formula works for n equals k, then it also works for n equals k plus 1. So we start with the sum formula for n equals k. We take the sum formula up here on the right, plug in k for n. That's all of this right here. Then we add one more term. So we take n equals k plus 1. So we have 5 to the k plus 1 minus 1. And we want to show that that equals to 1/4 times 5 to the k plus 1 minus 1. This algebra is a little trickier. So let's start with what we have. The first thing we're going to do is multiply out and simplify. So notice here we have 5k over 4 minus 1/4, and then simplifying this exponent, it's 5 to the k. And then we have 5 to the k plus 1 over 5 to the k plus 1 over 1/4 minus 1/4. So we have the minus 1/4 on both sides, but so let's group. Let's get a common denominator here so we can get everything over 4. So notice here we have 5k over 4 minus 1 over 4 plus 4 times 5k over 4. So we've gotten a common denominator for this part right here. Now notice we have 1 5k over 4 plus 4 more 5k over 4. So we have a total of 5 times 5k over 4. 5 times 5k over 4 by adding those two together. Now, one more step. If we can make this look like this, we're done. So recall that if we have the same base, 5 to the first times 5 to the k, we add the exponent. So we have 5 to the k plus 1 over 4 minus 1/4 equals 5 to the k plus 1 over 4 minus 1/4. Completed the proof. So I'll give you that back to look at for a second. This whole thing is on a PDF that you can print off. Probably should have done that prior to the video. I probably should have said that at the beginning of the video, but I'll try to remember to mention that in class. I don't really want to record this all over again, so I just wish I had done that. Have a nice day, and we'll do this more in class tomorrow. Don't expect to do this without a little practice with me tomorrow. Bye.